Let's look at the file write. So how does the file write work? We're going to, so this is part of the system, the write system call. If we're actually writing to a file, it's going to go through and we're writing to a inode. So what's going to happen? So we're going to go ahead and look at the maximum number of blocks that we can actually write into the file system. So we are going to look at the maximum operation block. So that's the maximum blocks you're allowed to use in any system call. Okay. Back up a second. That's the maximum you can use in any transaction within a system call. We're breaking our system call up into multiples, none of which will use more than max op blocks. Okay. We want to keep in mind though, so we're going to cut down how much we're actually writing based on this. And so max op blocks is the total number of blocks you can write, but there are some of the blocks that we might write are not going to be data blocks. So in fact, we are going to be writing the inode probably because we're updating the size. We might be updating the indirect block, right? Because we might go ahead and allocate a direct block. And then there's a block we're actually allocating. So this is just reserving some for all that. And so then we just go through a loop where what we're doing is beginning an operation and ending an operation. So this is the part I told you about where begin operation may block if there are too many operations already, such that it wouldn't be enough space to write in the log. How does it know that? Well, it just assumes that every call to begin op may need to use up to max op blocks. So it just looks at the total number of blocks that are in the log and sort of divides that up by max op blocks, and that says how many simultaneous begin ops or operations can be in progress at once. And then what's it going to do? It's going to go ahead and lock the inode in memory, write, and then update the offset in the inode. Unlock it, and then end the operation. Okay. So end operation may or may not do the commit, right, depending on whether there's still other operations that are in progress. How does the write work? Well, what the write work is going to do, right, we get given an inode, the source in userland of what's going to be written, the offset within the file where that starts, and then the total number of bytes. So we just go through updating by our particular M amount, right, which tells us how much we're writing. We figure out from BMAP which actually block that we're wanting to read from. We read that block, and then we figure out how much we can write in there, right? Because maybe our offset is such that we're only writing 1 byte into this block. We do a mem move into the buffer, and then we log write it. As we know, log write is just going to keep it in the cache, pin it, and write it in the in-memory list. Then we release our lock. We also then go ahead and update our size, and then update the inode. For beginning an operation, what are we going to do? Well, we have a lock on a log, which kind of makes sense, and then we're going to go ahead and go through this while loop. So if the log is in the middle of committing, then we're going to go ahead and sleep. And when we wake up, we're going to go ahead and come back to the loop and recheck again, as is the customary case for sleeping, right? Waking up from sleeping is considered a hint. It's not necessarily true that the condition you're waiting for has happened. So if we're not committing, then we're going to go through and we'll say, so for the middle of the committing, we certainly have to wait. Otherwise, we check and we see there's enough space. So we're going to look and we're going to see, okay, how many are in use now, right? This is the log header. So how many have already are already in our in-memory log, plus how many operations are still outstanding. Are there enough that if the other outstanding operations all wrote max op blocks and we wrote max op blocks, that we would still fit in log size? If not, we better wait. Otherwise, we'll go ahead and increment the number of outstanding and then continue on from begin op so that we can start writing. So this ensures, basically, we check ahead of time to make sure there will be enough space before we start. in log write itself, what happens? So we get given a buffer, and we look and we say, well, is this, have we already exceeded the maximum buffer size, if log size, in which case we're in trouble, we better panic. Otherwise, are the number of outstanding operations at least one? If not, something is wrong, right? We should be in the middle of an operation. So that's another sanity check here. These sanity checks are always really handy. Theoretically, they should never go off, but it's certainly much easier to find out something in your code is wrong by panicking and printing a message than just randomly letting things go bad. We'll acquire our log lock, and then we're going to go through and check and see, well, wait a second, is this block already in the log? That's certainly possible, right? Some other process may have, in another system call, may have written this block. The example I gave was if two different system calls are doing a create, they may still be allocating inodes in the same block. So if that's the case, then let's go ahead and just reuse that block number in the log. Okay. Otherwise, we will get to the end. And then I will tell us where we want to be writing in the log. And what we do is just mark our block number in there, and then increment the number of blocks, unless we're doing this log absorption. Go ahead and mark this as dirty, so that is our mark that this buffer is in use by an outstanding operation and should not be evicted. And finally, we'll release the log. So log write doesn't write, right? Log write doesn't actually write to the disk. Writing to the disk only happens as we are doing our last end of an operation. Let's take a look. So here's our end of an operation. We decrement the number, of course, acquire the lock to make sure no one else is messing with this, and then decrement the number of outstanding operations. And if we're at 0, then we need to be doing a commit. And we're going to mark that in the log. Otherwise, we're not the last, right? We're not the last, but it may be we were a operation which might have used max blocks per operation, but chose to only write, let's say, 1 block. So let's see what happens in the case where this was not the last outstanding operation. So what's going to happen? Let's look at this. So let's say S1 comes along, begins an operation. Is it going to succeed? Yes, because we're going to look at the number of blocks that are in the log, which will be 0, and we have 1 outstanding operation, which is 7. And so 1 outstanding operation can generate at most 7 blocks. That's certainly less than 25. For the same reason, when S2 comes along, it can start an operation. And S3 can come along and it can start an operation, because 3 outstanding operations, each at most 7 blocks per operation, is a total of 21, which is less than 25. When a 4th one comes along, it'll be blocked. It'll be blocked because it'll look and say, well, the 3 existing operations plus me is 4 times 7 is 28, which may exceed 25. Now, let's say what happens is S1 comes along, and S1 ends the operation. And it's written 2 blocks in the meantime. If we look at the log header, what does it look like? Well, it's going to basically have an n equals 2 in here, along with those block numbers written in here. So S4 is going to be woken up. So here, we wake up, and S4 then looks and it says, there are 2 blocks that have been written. There are 2 outstanding operations. If I were a third, 3 times 7 is 21, plus 2 is 23, that's less than 25. It can go ahead and continue. So that's why we have the wake up here. Then what happens? We come along, if we're doing a commit, that is, if we were the last operation, then we go ahead and commit, which we'll see in a moment, and then write to the log afterwards to adjust to say that we're no longer committing. and then wake up anyone who was waiting for us, and then release our lock. Let's look at what commit does. Commit basically looks and says, okay, if the log header n is greater than 0, because if it's less than 0, that means there was no writing that happened. Certainly there are system calls that might start an operation, realize there's no writing that needs to take place in the operation. It's going to write the log, right? So that writes them to disk. So it writes each of the items from the cache to the disk, writes the log header, and then goes ahead and installs. Okay. After write header is completed, that's when we are finally committed. Before the write head is completed, then if we were to have a crash, we would lose everything that's in this transaction. So we install the transaction, and then finally we have to rewrite the head to set it to 0, so that again, if we crash, we don't redo this transaction. xv6 does have some assumptions built into it. So the assumption is basically it's atomic. Either the write occurs directly or the write doesn't occur at all. So it's trusting that hard drive. So there's no partial writes. There's no wild writes where writes happen somewhere else on disk. There's no decay of any sectors. That is, no read errors when you're reading blocks. Also, there's no reading the wrong sector. So it's not possible that you ask for sector K and you actually get contents of K+1. We will see file systems in the future that actually can survive any of these. What do we like about xv6's log design? Well, it's got correctness, and that's because of the write head log. Right? It's got good disk throughput. Why? Because when we are writing our log blocks, we're batching those together. The problem is we're writing the blocks twice, so that is some difficulty. And it also supports concurrency because we can have multiple system calls running at once, adding their operations to a larger transaction. What's bad? So let's just write the good and the bad, right? Good, correctness. Reasonable throughput. And we also have concurrency. You can imagine that one choice might have been to just say every operation is its own transaction, and so therefore that would serialize all system call operations with regards to the disk. The bad parts, let's see, not very efficient, because we're writing every disk block twice. We log the entire block, even if we just change a couple bytes. So you could imagine a format that would be more specific. Instead of saying, here's the entire contents of block K, maybe we could say, here's block K and these 3 bytes in the middle of it. And we also have potential problems with operations that don't fit in the log. A really good example would be, let's say we want to unlink a file, right? That may dirty lots of blocks while we are truncating the file. So if we think about it, all of the indirect blocks would be touched within a particular operation. So all of those, including and the inode and perhaps the directory entry.